Hi everyone, welcome to this new course on dynamics, the second part of the engineering mechanics series. This course is meant for undergraduate students pursuing science or engineering disciplines. Anyone can attend this course, which will give you an idea of the basic concepts of dynamics and how we can apply them to everyday life. We shall be limiting our discussions to the basic concepts and problems in classical mechanics, also called as Newtonian mechanics. This course is free to access through the EC Civil for You channel on YouTube. Those who would like to get notifications regarding this class may please subscribe to this channel. Now, let me make a point clear. I would urge all students to renew the concepts of statics before continuing with this course, since it is one of the prerequisites of this course. Now, let us discuss what you will be covering in this series of lectures. The course is divided into 5 units or modules. They are Unit 1, Kinematics and Kinetics of Particles, Unit 2, Energy Principles and Impulse Momentum, Unit 3, Kinematics of Rigid Bodies, Unit 4, Kinetics of Rigid Bodies, Unit 5, Mechanical Vibrations and Central Force Motion. These are the topics which we shall be covering in this entire lecture series. I will be covering each of these units one by one from the next session onwards. I have arranged this course into 30 lectures, each having a duration of 30 to 40 minutes. To make the sessions productive, I shall be giving out some tasks that learners can try out before attending the next lecture, which will fortify your command over the subject. The suggested books for this course shall be Engineering Mechanics by Irving H. Shames. The second book, Engineering Mechanics Dynamics by J. L. Merriam and L. G. Craig. Then another book you can refer is The Vector Mechanics for Engineers by Ferdinand P. Beer. One other famous book is the one by R.C. Hibbeler. And then you can also refer to the book by Andrew Pytel. Now I shall be concentrating more on the reference Irving H. Shames. The course itself has been designed based on this textbook. This corresponding lecture shall be an introductory class of dynamics. So in this lecture I shall be covering 3 topics, namely what is dynamics, the basic concepts of dynamics, and third, the history of dynamics. Now, let us look into each of these in detail. Now, as you all know, engineering mechanics has been divided into 2 streams. There are statics and dynamics. Now, when we speak of statics, the simple term that comes into our mind is statics involves the study of bodies that are in equilibrium in relation to its frame of reference. I would repeat, statics is the study of bodies that are in equilibrium in relation to a frame of reference. Now, the word statics as such may imply stationary. but it is not. In statics, there are two aspects we are studying. One, the bodies can either be in rest or the bodies can be moving with constant velocity. Conveniently, the equilibrium of bodies that are in rest are called static equilibrium, and equilibrium of bodies that are in constant velocity is termed as dynamic equilibrium. So as such, when we hear the word statics, don't get confused that it involves only the study of bodies that are in rest. No, it involves both bodies that are in rest as well as bodies that are moving at constant velocity. Now, dynamics. Now, what do you mean by dynamics? It is the branch of mechanics that deals with the study of bodies that are in accelerated motion. I use this term specifically, accelerated motion. Why? Because in statics, if a body is moving if a body is at rest or moving with constant velocity, the net resultant force acting on that body is zero. In dynamics, that is not the case. Now, dynamics is usually studied in two specific branches. One is kinematics and the other is kinetics. Kinematics and kinetics. Now, kinematics involves the study of the motion parameters. The study of the motion parameters. Motion parameters means you can have the velocity, the acceleration, the time, the distance, the displacement, etc. So kinematics involves the study of the motion parameters without the reference to the forces that cause the motion. We will not be linking the motion parameters with the forces. We will not be linking the motion parameters with the forces. I'll give you an example. Now consider this car which is shown in your screen. The person is traveling on a highway. So he is concerned with the speed or the velocity of the car after say 100 kilometers if he is moving with a constant acceleration. Or he wants to know the distance covered in say time t equals 7 seconds or say time t equals 30 minutes. He wants to know the acceleration of the car. Suppose he is traveling at an acceleration that is continuously increasing. The acceleration can either be a function of velocity, it can be a function of time, it can be a function of distance. In all of these cases, we are concerned with only the motion parameters of the car without reference to the forces that cause the motion. Now consider another example. Consider this flywheel. Since this is a rotational motion, I can use the term the angular velocity. I can use the term angular displacement. So as such, I am concerned with the angular velocity, the angular acceleration, the angular displacement of this flying wheel after say time t equals 3 seconds, 4 seconds or whatever it is. So the case here is we are concerned only with the motion parameters of the body without taking into reference the forces that cause the motion. This is what comes under kinematics. Now in kinetics, in addition to the study of motion, we are also concerned with the forces that cause the motion. For example, suppose I say there is a rocket. I am concerned with the thrust of the engines that causes the corresponding rocket to accelerate upwards. I am not only concerned with the velocity or acceleration of the rocket, I am also concerned with the thrust of the rocket due to the bursting of these gases, and hence I can develop a relation between the motion of this vehicle or the rocket to the force, to the thrust offered by the combustion of the engines. Now, in a real sense, all bodies from the simplest single electron to the largest stars undergo some kind of motion relative to one another. Every engineering problem, from a simple moving car to the intricacies of the planetary motion, the space travel, involves motion. So taking into account all the parameters of motion is sometimes never feasible. So depending upon the frame of reference, depending upon the type of problem at hand, we make a great deal of approximations to reduce our calculations and arrive at the best solutions to our problems. Now, with that, we shall move on to the next topic, that is the basic concepts in dynamics. Now, here I would like to bring up two very important topics. One, the frame of reference, and second one, the particle and rigid body approximation. Now let us look at the frame of reference. Now, the position of a body in space is represented in terms of a reference system. A frame of reference is an arbitrary coordinate system with a physical reference or physical points that help to orient it or standardize the measurements within it. Now, all linear angular measurements are made with respect to that reference system. Since the motion parameters of a body, such as the velocity, the acceleration, are a function of the position of the body, they are always dependent upon the frame of reference from which they are being measured. So, in Newtonian mechanics, there exists a frame of reference called the inertial frame. The inertial frame of reference, or sometimes referred to as the Newtonian frame of reference or the Galilean reference frame, in which the Newton's laws of motion are valid with sufficient approximation or sufficient degree of accuracy. Any inertial frame can either be at rest or can move at a constant velocity. We shall be discussing regarding the frames of reference more about the frames of reference in the next lecture. But one thing you must remember is that in most design applications on the surface of the Earth, an inertial frame can be approximated by attaching the coordinate system to the surface of the Earth. One other important point is that in Newtonian mechanics, the time and mass, you have already studied the concept of time and mass in your statics. So time and mass are absolute. Now, the next topic we shall discuss today is particle rigid body approximation. In statics, you must have already covered the concept of a particle, a rigid body, a deformable body, etc. I'm not going to the physical aspects of such classification. However, I would like to point out specifically the characteristics of motion when we idealize a body either as a particle or as a rigid body. I would repeat, I am specifically concentrating on the characteristics of motion when we idealize any body as either to be a particle or that of a rigid body. Now, in many situations in mechanics, the size and shape of the body are not relevant to the motion described by the body. Since only the mass of a particle and not the physical geometry is taken into account, there is no rotation associated with particle. Any body, okay, or even of significant size, can be idealized to be a particle. It may be a car, an aeroplane, or even an entire planet. Let me give an example. Suppose I have a car that is traveling on a slope uphill as shown in this figure. I shall draw the corresponding car here. Now, I wish to know the parameters, the motion described by this car. Now, to make this problem simple, I have to consider some approximations. Now, what is the first approximation that I take into account? I assume or I concentrate the corresponding mass of the entire car to be acting at one single point. So you have the corresponding weight acting with respect to that point. Okay, now since the car is moving upwards, there is a force that is offered by the engines to move the car upwards. Now suppose I make an assumption that that corresponding force is also acting from the mass center. Next approximation, I neglect the wind drag forces. Now the wind drag forces depends upon the shape and size of the body. Okay, I also neglect the rotational inertia offered by the tires of the vehicle. We have idealized a body of significance, size and shape into a hypothetical particle. And all the forces are assumed to be acting from that particle. The motion of the mass center is all we need to know to characterize the motion of this car. This is the mass center. So any rotation about this corresponding mass center can be neglected. Do you understand? Means by saying that the bodies are analyzed as particles, we mean that only their motion as an entire unit is considered. Their motion as an entire unit is considered. Similarly, you can assume or we can idealize an aeroplane as a particle for describing its flight path. A planet may be described as a particle considering its motion around the sun. So there may be cases in which the rotation can be neglected, but there may be cases in which the rotation cannot be neglected. In such cases, bodies shall be treated as rigid bodies. So the motions, the types of motion that comes under rigid bodies involves the translational motion, includes rectilinear, curvilinear motions, and the rotational motion. And the combined effect of both of these as the general plane motion, which I'll be discussing regarding the general plane motion, the rotational motion in the later units. But as such, we must remember one thing in mind: there is rotation associated with a rigid body. In general case, there is rotation associated with a rigid body. So the treatment of a body either as a particle or as a rigid body, the treatment of a body either as a particle means the idealization of a body either to be a particle or a rigid body is based upon the motion described by the body as a whole. So based on this criteria, dynamics can be studied under two heads. We have dynamics of particles which involves kinematics and kinetics of particles, and you have the dynamics of rigid bodies. This also includes kinematics and kinetics of rigid bodies. So with that, I would end up the basic concepts, and then I will come up with the history. Moving on to the next topic, the history of dynamics. There are many renowned men in the past who have immensely contributed to the study of dynamics. Even though it may not be possible to name all of them, I would like to mention a few here. Remember one thing: many of these scientists have contributed to multiple fields, including physics, astronomy, mathematics, engineering, etc., etc. Now, let us draw the timeline. So I start with the 16th century, move on to 17th, 18th, and 19th. Timeline. Between 16th and the 17th centuries, in the mid of 16th to almost the mid of 17th, two famous thinkers, astronomers, physicists. One is the famous Galileo Galilei. I hope this name is familiar to all students of science and engineering. The great Italian astronomer and physicist who studied speed, velocity, gravity, free fall, inertia, projectile motion, pendulums, etc., etc. He is considered to be the father of modern science. Next, Johannes Kepler. Kepler also lived during the same time as Galileo. He was a German astronomer, mathematician, and astrologer. He gave us the laws of planetary motion and is credited to the modernization of Copernicus theory through his book Mysterium Cosmographicum. Between 17th and 18th centuries, the most famous personality is Isaac Newton. He was a mathematician, a physicist, and astronomer, and is one of the well-known scientists after Galileo. He laid the groundwork for dynamics and the three laws of motion and also the universal theory of gravitation. He used his theory of gravity to explain the Kepler's law of planetary motion. His book, the Philosophiae Naturalis Principia Mathematica, or the mathematical principles of natural philosophy, laid the foundations of classical mechanics. He used calculus extensively in his book and is also credited with the development of calculus along with Leibniz. The next famous scientist, mathematician during the 18th century is Leonhard Euler. This Swiss mathematician, physicist, astronomer contributed to dynamics in the forms of the rotational motion of rigid bodies. Euler is considered to be one of the most eminent mathematicians that dominated his influence in mathematical dynamics throughout the classical period. The Euler's laws of motion are the equations of motion which extends from Newton's law of motion from point particle to the rigid body motion. Between the 18th and 19th centuries, another great scientist, Joseph Louis Lagrange. He was an Italian mathematician, astronomer, and he formed the basis of the development of mathematical physics in the 19th century. His contributions include the principle of least work. Now, besides this, there are also many other important names that we ought to remember. We have Copernicus, who postulated that the sun was at the center of the universe rather than the earth. Then we have Tycho Brahe, who was a great astronomer and made a number of observations which were later used by Kepler to develop the laws of planetary motion. The next important personality, Alembert, the French mathematician and physicist. We know him for his studies in rigid body dynamics and fluid motion. D'Alembert, Euler, Lagrange were all during the same time, between the 18th and 19th centuries, and hence they had communicated each other for sharing of their knowledge. Besides this, we have Bernoulli, whose contribution to the fluid mechanics is well known, and we have Laplace. So these are some of the other personalities which we cannot neglect in the history of dynamics. I would say that the 17th and 18th centuries were the golden periods in the history of dynamics. For any subject, it is important to study the history. Our knowledge is built upon the advancements of such great personalities. Even if some of the ideas must have been falsified later, they had achieved the extraordinary during their time, and hence we are mere propagators of their contribution to mechanics. With this, I shall conclude my lecture. So, recapping, in this class we had dealt with three important topics: the basic idea of dynamics, the basic concepts of dynamics, and the history of dynamics. So thank you for your patience. Hope to see you in your next lecture. Thank you.